Today I started to work to a new project about vector sets. For now it's going to live in its own branch, but we will see if I will merge it. The problem is very simple. When you do vector similarity, for example, I want all the movies with a vector similar to the matrix, but what about if I can store attributes for each of my vector set element, like for example the year the movie was produced, and once I have the movie I could write filter dot year greater or equal 1995 and year up to 2000, for example, and it would filter it. What's the problem with this kind of approach? Is that if you have movies of many years, that's fine, it's okay. The HNSW search will basically get here some predicate function that will be the callback to understand if a given element can be accumulated or not. Basically it descends, and then the magic happens in search layer. And in search layer, here is the main loop. And here, instead of pushing the elements that we accumulate by similarity in the queue of candidates and the results will get filtered by this predicate. So basically, if you have, like in this example, many movies with many years, and almost every movies are distributed evenly in the years, that's okay, and it becomes a very useful feature. However, if there is just a single movie in 1995 and the user writes something like that and it wants 10 results, then the vanilla implementation, which tries to accumulate as much results as the user demanded, will basically block the system for a few seconds. So we have the keys asterisk problem in the realm of vector sets, because some users may not have in mind how this works and the cardinality issue, and will trigger a full scan. Instead, without having such a feature, what's cool is that you are forced to think out of the box and to, in the Redis way, to create a layout which is automatically designed for the kind of queries you want to run. So basically, instead of having this single key, you start to have many movies 1995, many movies 1996. You basically partition your data by year, and then when you make queries, you perform vector similarity against this, and so forth, and you merge the results back. However, I understand that this is more work, and users are going to need at least some symbol filter like that. To avoid the ON problem that I described above, one thing that's possible to do is to have a filter effort, AF, which maybe by default is like 10 times EF or something like that. So yeah, I scan for the filter that you provided, but as long as the vectors are still similar to the query, if they start to be too far away, I decide that I will not return everything. Otherwise, you can explicitly tell me filter EF I don't know, a large number, and this will do more work and will retrieve more results. So this is, I believe, a nice way in order to fix the first problem. However, here I don't want to expose a full scripting language just for this filtering. You know, I wrote a blog post a few days ago about the need for systems to scale down. 99% of people will just do symbol filtering like that, but I will also have things like category in this kind of stuff. So not just trivial things, but you can combine conditionals. You have parents for operators precedence and things like that. But still, it's much better if you can just filter like if it was an if expression, very simple one. So I started to work to some expression virtual machine. Basically, it compiles your expression to a set of tokens, and then it uses a stack machine in order to evaluate the expression. This is fast enough for most use cases, because you compile just one time. When you check the filter argument, you have like parse operator or select, parse number, parse string, and parse and so forth, and then the compilation function that I have yet to write will call parse number, parse based on the first character, calls one or the other thing. You know, I am not new to this kind of parsers. I actually released a number in my life. This is one, just a random one, the pickle parser. It's a very small interpreter in 500 lines of code, and 300 lines is the parser. I like handwritten parsers. So you end with a program which is just a stack of instructions and an instruction pointer, and you execute one after the other. However, what I like about all this is how do you write a program that evaluates an expression like 2 plus 3 times 5 less than 10. In high-level programming languages, you have eval. You call eval and this magically works. But how do you do it in a C language to let the user to write an expression, then you can parse it? Well, about that, I have an interesting story to tell you about the first time that I did this thing. Many years ago, 20 years ago, I wrote programming language which was another Tcl interpreter, but much better, called Gym Tcl. And I had to implement exp of Tcl. Tcl is like Lisp, basically. Normally command argument, just instead of these parents you have this and other semantical differences, but it's a lot Lisp-like. But in exp it becomes algol-like, so you could write this expression and it returns whatever you passed as an expression. So I had to implement this, and I didn't want to Google about how to do it. I often do this thing. Basically, I refuse the first time I'm doing something new. I refuse to check the literature, the right way to do it. I do it, then I check my result, and then I go to read the papers, the documentation, the books about the topic to see how the others did, and if the other approach is better, I integrate part of it. But this thing of always starting from scratch gives me the ability to think to some problem in a empty field with a fresh state of mind, and sometimes this helps a lot. For example, when I wrote Redis, I didn't know memcached existed. That's very funny, but still it's part of this way of working. So when I studied a bit the problem and it clicked, I said, oh my god, this is so cool. Also consider that I was a fan of Fort of stack machines and languages already. So when I wrote this, and I was so happy that it was so easy, so stack-like, and so this is what you do. You start with the assumption that there are operators that are at a different level of precedence. So multiplications are done before additions and so forth. Okay, but basically you take this expression and split it in tokens. Okay, one token after the other, which is exactly the structure that my expressions will have once they are tokenized and pushed on the stack. And you start, and then you have a values stack and an operators stack. You start and consume the first one, 2. It's a value, so I push it in the values stack. Then I parse another one, it's an operator, and I push it here. Then there is another... when I push the operator, I check before pushing it if there are other operators already in the stack. But in this case, there is nothing. So I cannot execute any part of my past expression. This is the first operator. So I just push it here. Then there is another value, and I push it on the stack. Oh, now it's interesting. Now I have a new operator. But since multiplication is at a higher level than addition, I will just push the operation on the stack. Otherwise, if they were swapped and my expression was before the multiplication then the addition, the fact that here was here and now there is a lower level operator will trigger the execution of the multiplication immediately, but that's not the case. So far nothing, because I only execute the operations for which are of a lower precedence compared to the one that I just pushed. Now I have 5 and I push it on the values. Oh, finally now I have an operator which has a very at a very lower level compared to these two. So in order to push less than in the stack, before I have to execute all the operations which have a level which is higher than it, which is bot. So here there is a multiplication. I just apply the multiplication to the top elements on the stack. And here also less than is also at a lower precedence than plus. So I have to execute this one as well. And I finally can push this on the stack. Then I have 10. And then I have end of file. And this will also, like an operator, will trigger everything is in the operator stack. So basically I compute is 17 less than 10. It will evaluate to false, and this will be the result of my expression. Now, what's super cool about all this is that it's very easy to also implement parents. Imagine that I have something like that. So this will force the addition to be made immediately, even if after there is the multiplication. So also I tokenize again. So what I do is I put my operator on the stack, then 2, then plus, because this is at the highest precedence possible, then 3, then I have the closing parent, which triggers the execution of all the operations up to the matching parents. So basically I have to execute this one and I remove this one, and the result is 5. Then I process this, then I process this, then I process this, and this triggers the execution of this part, and then I process this, and then 25 is less than 10, and it's true. Okay, so it's very, very simple rules to apply, and with these simple rules cascading, with the cascading effects of these simple rules, I can write any kind of operation with nested stuff, everything I want, and I find this to be super cool. So let's see how. Okay, this is my table. I have op name, op len, opcode, precedence, but precedence, and I have the length for simple matching here, and then the precedence, which is very high for the parents, and then it is lower. Okay, this is I will do special handling here in this case. Okay, I think I need absolutely to do special. Parents cannot happen automatically because I have basically to match the other one, I believe. I will see if I find a way to generalize it to the point that I don't do anything special, like probably possible. It's probably possible. Cool. But I will show you probably the full implementation at the end. The problem with this kind of features is to communicate them to the user efficiently. I mean, if you understand what filter is and what it does, and the fact that the greedy search in the HNSW graph continues still some effort is performed, then it's a cool feature to have. Because I believe that in many use cases you don't need hybrid vector similarity search, but in certain use cases you need, and in certain use cases you don't want to split the vectors in this way. So basically I plan to have things like that, like v set attr, my vector set, my element here, and so forth. Like if each element of the vector set is basically a hash also, and there will be commands to get the attributes, and also vgetAll or vfetch to see all the attributes associated with a given element. But for now I will implement it, see how the work goes, if I like it, how it performs in practice and in real datasets. And this of the movies is a handy one in order to do some tests, and I will decide if to really implement it or not. Bye, have a nice day.